Good morning, class. We will now move on to section 8.2, which talks about the student's t-distribution. Recall that in the last section, we assumed we knew the value sigma. This was our population standard deviation. However, the only way you would know the population standard deviation is to know every value in the population. With this knowledge, you could calculate any parameter you needed, and there would be no need to estimate anything. Rarely do we actually know the population standard deviation. As a result, two facts are crucial: the distribution of the population and the size of the sample. If either the population is normally distributed or the sample size is sufficiently large, then another distribution called the student's t-distribution may be used to calculate the margin of error for a population mean when the population standard deviation, sigma, is unknown. The student's t-distribution is another important continuous probability distribution. It is similar to the standard normal distribution in that it too is bell-shaped and centered at the value 0. However, the t-distribution has more area, this is a typo, has more area under the tails or fatter tails on each end. Also, whereas the standard normal distribution has two parameters that describe its shape, remember the mean and the standard deviation, right? The mean tells us where it's centered, and the standard deviation tells us how flat or how peaked it is. The t-distribution has only one parameter, and this parameter is what we call the degrees of freedom, and we denote this by df, for degrees of freedom. As the number of degrees of freedom increase, the t-distribution curves approach the shape of the normal curve. So notice that the normal curve is given here in red, and if we look at a student's t-distribution with degrees of freedom 3, notice that the degrees of freedom 3 has very fat tails. But if we increase our degrees of freedom and look at the green curve, notice that the tails shrink and it looks more closely resembling the standard normal, the z distribution here. Okay, so a look at table C. So this is our last table that you needed to print out, and if you haven't done so, go back to our module 0, our course orientation, and you'll find our tables, our statistical tables, where you can print them out. So a look at table C shows us that the interior of the student's t-distribution table gives the t-values. So if we look at the inside, these are all of the t-values associated with gives the t-values associated with the particular areas under the curve. So notice on the outside, we have our degrees of freedom and our areas in the tails. So notice it gives us area in one tail, or it gives us the option for area in two tails. This is the reverse of a standard normal distribution table. Remember that the z table gave the areas in the middle and the boundary values on the outside. Those were our critical z values. So a fun fact, William Gossett published his work regarding the t-distribution in 1908 while working at the Guinness Brewery in Dublin, Ireland. Because his employer required him to publish under a pseudonym, Gossett chose the name Student. Over a century later, Gossett's work lives on, as does the pseudonym Student's t-distribution. So a little history about where this t-distribution came from. So let's look at some examples to see how we can use table C. And once we get through this section, we're going to come back to our confidence intervals and talk about the case when sigma is unknown. And in that case, we're going to utilize the student's t-distribution. So our first example, find the value of t 0.025 for the t-distribution with 25 degrees of freedom. In general, the value of t such that an area of alpha is to the right of t is denoted by t alpha, okay? So in this case, t alpha is our boundary value where alpha, the subscript, is the area to the right, okay? So again, a little different than what we're used to with our z distribution. Our z distribution gave values, areas to the left, okay? So in this case, this notation means area to the right. So looking back at the original problem, we had t 0.025. So this tells us 0.025 is the area to the right of our t. The number of degrees of freedom is listed in the first column, and the value of 0.025 tells us to use the column for an area in one tail because it's to the right, so it's one tail. So what we do is we find degrees of freedom, 25, and we look at the area to the right, or just area in one tail, 0.025, and we line those up, and we get a t value of 2.060. Let's look at another example. So find the value of t for a t-distribution with now 11 degrees of freedom, such that the area under the curve to the left is 0.05. So if we visualize this, remember that our t-distribution is a bell-shaped symmetric curve, so we can draw it very similar to the normal curve. And we want to find this t value, this boundary value, where 0.05 of the area is to the left of this value. Notice that our table only gives positive t values. That means the table only gives us t values that correspond to an area to the right, right? And remember, we denote these by t sub alpha. Because the distribution, though, is symmetric, we can look up the t value for an area of 0.05 under the curve to the right of t, okay? So we're going to look up t 0.05. So we use 11 degrees of freedom, and our area in one tail is 0.050, and we're going to see that we get t equals 1.796. However, since the given area is to the left, the t value needs to be negative. Remember that the center of the t distribution, just like the z distribution, is 0. So all numbers to the left of 0 are negative, and all numbers to the right of 0 are positive. So for this example, we want negative t 0.05 or negative 1.796. So to the right, we use the value given in the table using area in one tail. To the left, we again use the area in one tail, but when we find the value in our table, we need to make it negative. That's the trick. Let's look at another example. Find the value of t for a t-distribution with 7 degrees of freedom such that the area to the left of negative t alpha over 2 plus the area to the right of t alpha over 2 is 0.02, okay? So again, if you want, you can draw a quick picture of this. So we have a boundary value, negative t alpha over 2, and we have another boundary value, t alpha over 2, and we're saying that the area to the left plus the area to the right is 0.02. But notice that these are the same number, just one is positive and one is negative. So by symmetry, these areas have to be equal. So that means each area is going to be half of this area. So we get 0.01 in each of the tails. This is what we call a two-tailed problem. Because the given area 0.02 is divided between both sides of the distribution. When looking up the t value in the table, we simply find the given area in the row labeled area in 2 tails. So remember that the degrees of freedom was 7, but now since we're talking about the area to the left and to the right, we're looking at the area in 2 tails, and we said that the sum was 0.02, and we matched those, we lined those up in our table, and we get t equals 2.998. Let's look at one more example for this section. Find the critical value for t for a t distribution with 29 degrees of freedom such that the area between negative t alpha over 2 and positive t alpha over 2 is 99%. Okay? So notice that we have negative t alpha over 2 and positive t alpha over 2, and the area in the middle is 99%. Notice this looks very similar to our confidence setup, right? Confidence is the middle area. So this, a problem like this is going to help us in the next section, okay? So since 99% of the area under the curve is in the middle, that leaves 1% or 0.01 of the area remaining. Remember that the complement is 1 minus this. So if we take 1 minus 0.99, we get the area here plus the area here, and we get that to be 0.01. This is the area remaining in the 2 tails, right? So we're going to use our table C with area in 2 tails. We look across the row, we're given that degrees of freedom is 29, and we're focusing on area in 2 tails. Our area in 2 tails is 0.01, and we line these up and we get t equals 2.756 here. Okay, so a few notes. We cannot utilize our calculator if we are using our smartphone app, since this requires us to purchase an upgrade. And I don't want you guys to purchase anything in this class. You've already purchased the Hawks learning software. So, however, if you do have a TI-84 graphing calculator, you can look at your Hawks, when you log into your Hawks in your Learn section, or in your, I believe it's in your Module 0, or your Start Here page on Canvas. I forget which one it's in. There's a link to videos on how to, example videos and publisher videos by Hawks. But in the Learn section of your Hawks homework, they document how to utilize your TI-84. So if you're interested, you can look into that, or again, post in our discussion board, or send me an email and I can help you figure out, how do you utilize your TI-84 app. And that's okay if you want, but if you're utilizing the smartphone app, we're just going to do it using Table C. And then finally, if the number of degrees of freedom you desire is not listed, sometimes this happens, we can only list so many in Table C, we simply use the entry for the next smaller number of degrees of freedom. So if it's not listed in the table, go to the closest one that's above it, right? The smaller one, because as we move down, the degrees of freedom increases.